Hello, students. Let me begin with a question. How do we make a compound like chloroform in the lab or ethyl chloride in industry? The answer lies in the clever chemistry of preparing halolcanes. And LT, break time is equal to 0.5 S and GT. Halolcanes are valuable intermediates in organic synthesis, and we can prepare them in several ways, from alcohols, hydrocarbons, alkenes, or even by exchanging halogen atoms. The method we choose depends on which halogen we want to introduce and how stable we want the product to be. And LT, break time is equal to 0.5 S and GT. Remember, methods that work in a small-scale laboratory experiment may not always be suitable for industry, and halogenes require entirely different methods because of the strong carbon-oxygen bond in phenols. So today, let's walk through these major routes of preparation.
Have you ever wondered how the simple alcohols we use in labs can be transformed into powerful building blocks of medicines and plastics? The key lies in replacing the OH group of alcohols with halogens to form haloalkanes. Alcohols react with hydrogen halides to form haloalkanes. The general reaction is ROH plus HX gives RX plus H2O. Let's see how this works for different types of alcohols. For a primary alcohol, RCH, 2OH plus HCl in the presence of zinc chloride gives RCH2Cl plus H2O. For a secondary alcohol, R2CHOH plus HCl with zinc chloride gives R2CClH plus H2O. For a tertiary alcohol, R3COH plus HCl with zinc chloride gives R3CCl plus H2O. Finally, alkyl iodides are obtained by heating alcohols with sodium iodide or potassium iodide in phosphoric acid, H3PO4. This simple replacement of the OH group is one of the most important ways alcohols are converted into useful compounds. Another method is to start directly with hydrocarbons. Alkanes, when treated with chlorine or bromine in the presence of ultraviolet light or heat, undergo free radical halogenation. For example, methane reacts with chlorine under ultraviolet light to form chloromethane and hydrogen chloride, written as CH4 plus Kl2 in the presence of UV light gives CH3 Kl plus HCl. The mechanism is a classic free radical chain process, initiation, propagation, and termination. But here's the catch. The reaction produces mixtures of mono and polyhalogenated products. Separating these is tricky, so the yield of any single haloalkane is low. That's why this method is excellent for demonstrating free radical chemistry in the lab, but not practical for industry. Alkenes are also excellent starting materials. They undergo addition reactions with hydrogen halides to form haloalkanes. Take propene, CH3, CH double bond, CH2. When it reacts with hydrogen bromide, the product is isopropyl bromide or 2-bromopropane. The reaction follows Markovnikov's rule, which says that the halogen atom attaches to the carbon with fewer hydrogens. In short, the rich get richer. Alkenes can also add halogen molecules directly. For example, bromine dissolved in carbon tetrachloride adds across the double bond to form vicinal dibromides. Interestingly, the disappearance of bromine's reddish-brown color is used as a test for unsaturation. So, from alkenes, we can prepare both monohaloalkanes and vicinaldehydes depending on the reagent. Sometimes the haloalkane we obtain first is not the one we really want. To solve this, we use halogen exchange reactions. The general reaction is RCH2X plus sodium iodide in dry acetone gives RCH2I plus sodium X. A special case is the Finkelstein reaction. Here, RCl plus sodium iodide in acetone gives Ri plus sodium chloride. The sodium chloride that forms is insoluble and precipitates out, which drives the reaction forward. Next, let's talk about preparing alkyl fluorides. They are made by heating alkyl chlorides or bromides with metallic fluorides. For example, C2H5Cl plus sodium fluoride on heating gives C2H5F plus sodium chloride. Another method is the Schwartz reaction. In this case, RCl reacts with silver fluoride to give RF plus silver chloride. So, halogen exchange allows us to convert one haloalkane into another, depending on which halogen we need for synthesis. Let's solve an advanced example. If we chlorinate 2-methylbutane using chlorine in the presence of ultraviolet light, how many monochloroisomers will we get? This molecule has 4 different types of hydrogen atoms, so we expect 4 distinct products. First, chlorination at the terminal carbon gives 1-chloro-2-methylbutane. Second, chlorination at another carbon gives 3-chloro-2-methylbutane. Third, chlorination at the tertiary carbon gives 2-chloro-2-methylbutane. And finally, chlorination at another unique position gives the 4th monochloro derivative. So, from 2-methylbutane, 4 distinct monochloroisomers can be formed. This illustrates the non-selective nature of free radical halogenation. Instead of one product, we often get mixtures. So, to wrap up our session, haloalkanes can be prepared in several ways, from alcohols by replacing the hydroxyl group with a halogen using hydrogen halides, thionyl chloride, or phosphorus halides, from hydrocarbons by free radical halogenation, though it gives mixtures, from alkenes by addition of hydrogen halides or halogen molecules, following Markovnikov's rule, and by halogen exchange with the Finkelstein and Schwartz reactions. Each method has its strengths and limitations. For pure haloalkanes, reactions using thionyl chloride or halogen exchange are most reliable. For demonstrations, free radical halogenation is excellent. So remember, the method you choose must match the substrate, the halogen, and the desired product purity. I hope this session helped you see how chemistry offers many paths to the same destination, the versatile haloalkanes. Catch you in the next class with more fascinating insights into organic chemistry.